just wait for a few more minutes to see if somebody else joins and then we'll start. Okay, let's start. Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we'll go over the questions of week 10 and then some content from week 11. So let's start. So just a recap of all that we've done in the past couple of weeks. So we introduced dynamic stability. We had started with static stability and then we moved on to dynamic stability. And then we saw two new terms added to our CL and CM equations corresponding to Q and alpha dot respectively. So two new terms. And we saw why these terms came into play, the moment arm, the lift force generated, and how it contributes towards dynamic stability. So all of these terms came from that, their respective derivatives and for the lift and the moment. Then we saw how it compares to a typical second order system, a spring mass damper system, where Cm alpha is like the stiffness coefficient of a spring mass damper system. So it resists the tendency towards a disturbance, resists the tendency towards a change from its equilibrium. Then what we had was CMQ. CMQ is similar to the damping coefficient of a spring mass damper system, where its value tells us whether the system will come towards equilibrium or it will go further away from equilibrium, and if it comes towards equilibrium, then how its response will be over time. So dynamic stability deals with the response towards a disturbance over time. Does it go away from equilibrium, comes back to equilibrium over a period of time, and how it comes back to equilibrium. Alright. Then we saw the different frames of references used to come up with the equations of motion for dynamic equations of motion. So we take inertial and body frames for this representation because our equations of motion are only valid in the inertial frame, but our data is collected in the body frame mostly, right? So what are the different forces that we have? Yeah, so the different forces that we have in our system are aerodynamic, gravitational and propulsive. Aerodynamic, we have lift and drag. Gravitational force, it's well known to us, and propulsive is the thrust force. Now we plugged in these values using these frames and forces. We then came up with the equations of moment. There shouldn't be an M here. Okay. So we have the equation of motion for force and the moments. And then we saw the transport theorem that relates the derivatives in the body frame to the inertial frame. This makes conversion from the body frame to inertial frame smooth, because most of the quantities that we measure are in the body frame, but our equations of motion are only valid in the inertial reference frame. Then we saw the individual components of the forces and the moments and all the other components, the vector components in the inertial frame. So that's given here. Then we just expanded the two equations. So expanding the force gives you three separate force equations in three directions. Similarly for the moment, these are the expanded versions, and you can see the three forces here. So aerodynamic, propulsive and gravitational. Now then we introduced one method of attitude representation, which is the Euler angles, and then I mentioned that this theta and psi are not to be confused with pitch and yaw of the aircraft. These are different. These Euler angles are different. They are with respect to the reference frame, inertial reference frame. Okay. Yeah. And these angles mainly come about when we represent the gravitational forces and when we represent the angular velocities PQR. Alright. Then we moved into longitudinal dynamic stability. So we took the three equations that help us define the longitudinal dynamic stability. So we have equations for U dot, W dot and Q dot. Alright, so this is supposed to be Z. Right. So U dot, W dot and Q dot, these give us the longitudinal dynamic stability equations. So then we introduced the small perturbation theory. What this said was that you pick an equilibrium point and then you subject it, assume that there is a small perturbation applied to it. So what is the equilibrium point for an aircraft? What is the equilibrium point for an aircraft in the longitudinal dynamic sense? So it is the trim condition, right? So trim is when trim or equilibrium, they're all synonymous terms. And in our case, it is when sum of forces and moments are zero. So in our case, it will be when lift equals to drag, lift equals to weight and thrust equal to drag. So it's the trim when lift equals weight and thrust equals drag. Right, so this is one of the equilibrium conditions for the aircraft. So all of these terms with the subscript 1 are the values at equilibrium, and all of the terms with the small alphabet, small u, small v, small w, all of them correspond to the small perturbations that are applied. Now using these equations, using these assumptions, you rewrite the equations, and then to simplify it further, we take the stability axis. This was discussed yesterday. So you take the stability axis along the velocity direction, because most of your terms are measured either parallel or perpendicular to your velocity axis. So you take your stability axis along that direction to greatly simplify your equation. And after all these assumptions and simplification, we get these three equations to be the longitudinal dynamic equations. Using these three, we can assess the dynamic stability of longitudinal dynamic stability of an aircraft. Okay. Then all of those terms were individually expanded in terms of their derivatives with respect to each of the terms. Now in the fx equation, you can see that terms pertaining to alpha dot and q are not present. This is because in the x direction it is very negligible. They do have contributions in the x direction, but their contributions are very negligible and can be ignored safely. So these two terms, the derivatives corresponding to q and alpha dot, are absent in the x direction force, but it's very relevant in the z direction and the moment. Right, so we start with the derivatives in the x direction. So we have these three derivatives. Upon substituting, you get u dot equations. We need u dot, w dot and q dot. These are our three terms that define dynamic stability in the longitudinal direction. And you can write it in a compact form in this manner, where xu, x alpha, x delta e are, so this is xu, this would be x alpha, this would be x delta e, and you can just write it in a compact form. Similarly, we do it for the fz case. So each of the derivatives are derived, and I think I mentioned this even yesterday. So why is there an alpha dot? Why can't we just have q? Why do we have to have an alpha dot? Because when we give the command for increasing the alpha, it doesn't really get there immediately. Over time it reaches there. There's a slight slow build-up of the lift for it to reach this alpha. So there is the rate of change of angle of attack, which is why you have an alpha dot. Another reason is that downwash reduces alpha at the tail. So there is a change in the angle of attack with time due to both build-up of lift and due to downwash. That is why we have an alpha dot and q. We have both of them. It's not just q. Similar to the previous case, you substitute the derivatives into the equation, and you have an equation for w dot. You can write it in a compact form just as in the previous case. You can have, like we had xu, x alpha, you can have similar compact forms here. So you can write these terms to simplify it. Alright. Now the third and the final equation is the moment equation. Again, these derivatives were derived, and you can write it in a simplified fashion for q dot. This is the third equation of motion that is necessary to define the dynamic stability. Now you put all of these three equations in a compact form together in the matrix form. Okay, so all of these were the three equations that we just saw. Now putting it in a matrix form and applying Laplace transform on it gives you this need a representation to assess the stability. So this is in the form of ax equals b, right? So this is x, this entire thing is a, and this is b, and this is in a form which helps you to analyze stability using the various ways that we have studied in the other subjects, right? So you have Routh criteria and similar such things. So you apply the Laplace, take q as theta dot and then apply the Laplace transform. So you get q of s equals s theta of s, right? So and then you substitute it into these equations to get this compact form. All right. Now when you, so to assess the stability you need the characteristic equation. The characteristic equation is nothing but determinant of A is equal to 0. Let's just take this as A bar because later you'll have other coefficients. Alright, so determinant of this matrix is equal to 0. That equation gives you the characteristic equation for this system. That equation will be a fourth order system. So you can see that there's an S here, and then an S square here. So it will be a fourth order system. So it will be in this form. And now we know from the Routh criteria what are the conditions that are necessary for the system to be stable. So the first condition is that all of these coefficients must be positive. So A, B, C, D, E should be greater than 0. Then we construct the Routh table, and the conditions imposed that we get from the Routh table are that all the quantities in the first column of the Routh table must be positive. Now from that we get the other two conditions. This is from the Routh table. Right? So these are the three conditions that we get to ensure that the system is stable. Now when we take the roots of the system, they almost always come in pairs, two pairs of complex conjugates. Alright? So there are four roots to this system, and they come in the form of two pairs of complex conjugate. So you have something like A plus or minus IB, C plus or minus ID. So these are the roots of the system. Now one pair of them corresponds to the short period mode, and the other pair corresponds to the long period or the phugoid mode. Okay, both of these, what it implies is that there is an oscillatory response. So over time the system responds, the dynamic response of the system is oscillatory in nature. Now if say magnitude of A is greater than magnitude of C, can you tell me which of these pairs correspond to short period? If the magnitude of A is greater than the magnitude of C, which of these pairs correspond to short period, which of these pairs correspond to long period? Okay, so the greater in magnitude term corresponds to short period, and this one is the long period. Now for stability, should A and C be greater than 0 or less than 0? From what we have learned, should the roots, the positive or the real part of the root, should it be positive or negative? should be negative, right? So all the roots on the left half of the plane gives you stability. So now these two pairs of roots can individually be used to write a second order system, right? So you have two pairs of roots and each pair can be used to represent a typical second order system, for which we have this equation. So mx double dot is supposed to be t, right? Mx double dot plus cx dot plus kx equals f of t. So this is a typical second order system whose characteristic equation is given in this manner, roots are given in this manner, and then you have the natural frequency, damping ratio, and the equation of motion in this manner. So each of those pairs of roots correspond to a typical second order system. Alright? Okay, now let's look at the questions of week 10. So given this characteristic equation, how do you find the roots? So finding the roots is a little tricky. So since you're given the options, you can just plug in the options and come up with the right answer. Right? So you can plug in each pair of roots and see which satisfies the equation, and then you'll have your right answer. This is easier than solving it. So I hope you've all solved the assignment, so you'll be able to answer this quickly. Just plug in all the pairs and see which one satisfies the equation. So the second set of roots actually satisfy the equation that is given in the question. Alright, so let's go to the next question. The damping coefficient for the roots are, how do we do this? Write the equation, equate it to a typical second order system, and then find out the damping ratio. So how do we write the equation when the roots are given? You have s square minus sum of roots into s plus product of roots equals 0. So in our case, what would it be? And equated to the typical second order system. So that is 2 eta omega n s plus omega n square equals 0. Right? So in our case, what would it be? So our roots were minus 1.15 plus or minus 2.7. Right? So this was the first pair. Just plug it in and see what we get. We get you equate it, you get omega n square is and so the second term you have 2.1.1595, and so you have eta to be 0.3838. So this is 1. Now you plug in the second pair of roots. What were they? 0.0072 plus or minus do the similar thing. You get s square plus 2. you equate it to this second order equation. So which one is the option? It's this. Next question is, what are the natural frequencies? We just found the natural frequencies. So they were 3.02 and 0.09. So this one. So now they've given you an ordinary differential equation y dash minus y equals e raised to 3t, and the initial condition y not equals 2, and they've asked you to find out the Laplace transform. It's a straightforward question, right? So you can just directly apply the Laplace transform. It is s y of s minus y of 0 minus y of s equals e raised to 3t, the Laplace transform is 1 minus s minus 3. Now you simplify it, what we get? We get s minus 1 y of s 0 equals 1 by minus 2, and you get y of s is so which option is this? 2. It's this one, right? So that was straightforward. Then they've asked you the solution to the differential equation y of t. How do we go about doing this? So we have y of s. We just found it to be 2 by s minus 1 plus 1 by s minus 1 plus minus 3, and they've asked us to find y of t. Okay, yes. How do we go about doing this? Now you take the y of s equation as partial fractions, and then you can simply apply the inverse Laplace transform and find it. So just write y of s, that's 2 by s minus 1 plus a by s minus 1 plus b by s minus 3. Now we have to find out a and b. So you can just take s equals 1, and then for the next case s equals 3, and then you'll be able to find out a and b. So please try doing it, and then we can find it. Alright, so a, I get it to be around 1 by 2. This is plus 1 by 2. So if I just substitute it, I get 2 by s minus 1 minus 1 by s minus 1 by 2. And I have plus 1 by 2 s minus 3. So on simplification it is 3 by 2 s minus 1 plus 1 by 2 s minus 3. Now if I apply the inverse Laplace transform, I'll get the direct answer. Y of t is 3 by 2 e raised to t plus 1 by to e raised to 3t, which is option 2. Yes, it's the right answer. Alright. So now let's go to the next question. This is just something similar to what we have done before. Since we have already done this should be easy to find. So if the equation is y double dash is minus 5y dash plus 6y and you have two sets of initial conditions, what will be y of t, the solution of this differential equation? Just try doing it and then we'll do it together. So you can just take, this is similar to some question that we did yesterday. You just take y equals e raised to at, and this will help you with the characteristic equation, and then you'll be able to find out. So from here we can easily get the characteristic equation, right? So you get a square minus small quantity, so you can easily get a minus 3, a minus 2 equals 0. So your equation is the solution. Your roots are 2 and 3, so your solution is y equals c1 e raised to 2t plus c2 e raised to 3t. And c1 and c2 you can find from the two initial conditions, two equations, two variables, so you can easily find it. Just use the initial conditions c1 and c2, and then you'll have your final solution. Let's try to find out c1 and c2 from the initial conditions. Y naught equals 2 and y derivative of y naught equals 2. Actually very straightforward. So you get c1 equals 4 and c2 equals minus 2. So your solution will be y equals 4 e power 2t minus 2 e power 3t, so which is option number 4. So this is the solution. Next, this was the question that we discussed yesterday. So the simple way to find out this response was to find out the damping ratio and see if it's overdamped, underdamped, critically damped, or undamped, right? So from this denominator, you can easily find out omega n and epsilon. How do we do that? So s square plus 2 eta omega n s plus omega n squared equals 0. So from this we have omega n is 3 and eta is 1.5. So what does it mean? That means it is overdamped, undamped. What is it? 1.5. Damping ratio 1.5. It's overdamped. Okay, so that response comes here. This is critically damped and this is overdamped. So this is the right answer. This was just a simple way to find it, but there is a method to actually find out the equation also. So I had asked if you could come up with the solution. So if you could just solve this and tell me how you did it, and then we'll proceed to solve it together. So they've given you RFS, CFS, and they've asked you to find out C of t. That is basically the question, right? can use the omega and damping ratio values that we just found to help you with coming up with the equations. So it's the same fashion as the previous questions. So you come up with the characteristic equation, try to split it nicely. So this is a little difficult to split because it's not, so the previous question had a 5s, so you could easily split it into 3 and 2. But in this case it's a little tricky, so 9s cannot be so easily split. So you can try to come up with a better way to split the equations, and then you can just apply inverse Laplace transform and get the equation. Start it and then we can see if you can proceed. So what we need to do is CFS by RFS, that is the transfer function that is given in the question, which is 9 by s square plus 9s plus 9, right? And where RFS is given as function s, and we found out eta to be 1.5 and omega n to be 3, and they've asked you to find out C of t. This is what is asked. So now we need to nicely split the denominator. So what we do for that? S squared plus 9s plus 9 is, so just write it in terms of the damping ratio in that form. So S squared plus 2 into 1.5 into 3 s plus 3 squared. Now what do we do to get a neat split? Just add and subtract the term in the middle. So you get a plus b, to ensure that you get something like a plus b whole square. Okay, so you just add and subtract 1.5 into 3 whole square minus 1.5 into 3 whole square. So what happens now is that you get s square plus 2 into 1.5 into 3s plus 1.5 into 3 the whole square. So this is 1, and then you have 3 squared minus 1.5 into 3 whole squared. So you have two terms where this is a plus b the whole squared. So you can have a nice neat split. So what comes is s plus 1.5 into 3 the whole squared. Let's write this neatly. And you have minus, so I'm just taking it common, 3 squared 1.5 squared minus 1, right? So now you can write your C of s. Just take C of s because we need to apply inverse Laplace transform on C of s to get C of t. So you get C of s equals 1 by s into, you can write the numerator as 3 squared, denominator will be s plus 1.5 into 3 squared minus, right? So what we get here is a square minus b square. So this is a square minus b square, which is a plus b into a minus b, right? So you get it in that neat form. So what you get is, let me just erase this. one term, a plus b into a minus b. Right? So now you can just have a partial fraction method and then find out a, b, c. So you have a by s plus b by, I've just simplified the term, so s plus 7.854 plus c by s plus 1.146. Our only task that remains is to find out a, b and c, and then it's a simple inverse Laplace transform, and then you can get it. A, b and c. You can just substitute the values and find out a, b, c quickly, and then you can find out the equation. This is very straightforward, so I'm just going to write down the ABC values that I've found. So A is obviously 1, and B I'm getting it as 0.1708, and C is minus 1.1708. So now you just apply inverse Laplace transform and you will get this equation, right? This is straightforward. Now let's go to the next question that we had seen yesterday. Again, we applied the similar method and found out the right answer. So it was omega n comes out to be 3, and here in this case eta is 1, so that means it's critically damped. This is critically damped, so this is the right response. But similar to the previous question, you can also find the exact equation. How do we go about doing that? Again, you just need to split the denominator in a nice neat fashion. This is easier than the previous case. So you have again C of S by R of S is 9 by squared plus 6S plus 9. So your C of S is 1 by S, where R of S is 1 by S, alright? So you have 9 by S squared plus 6S plus 9. Here the denominator can be easily split as S by S plus 3, S plus 3. Right? So this is very easily, you can split it easily. Again, apply partial fractions, find out A, B, C, and you'll get the equation, right? So you get A by S plus B by S plus 3 plus C by S plus 3 whole squared. And you need to find out A, B, C. Get the right answer. So A is again 1. I'm just going to write this. So it's just minus 1 and minus 3. And then you apply inverse Laplace transform. So C of t will give you 1 minus e raised to. So you have the roots, repeated roots, which is why you have it's critically damped, right? So both those roots 3, repeated roots at 3. So you have e raised to minus 3t minus 3 t e raised to minus 3t. Alright, so this is the equation that you will get. You can see the same equation here. This is the method to solve it analytically. final question that we had seen yesterday was s squared plus 9. So in this case again omega n is the same, is 3, but eta is 0. So what does it mean? It's not damped, undamped. How does an undamped system behave? It continues its oscillation. So this is the right answer. It's undamped. Now, similar to the previous case, you can find out the equation of motion. This is again easier compared to the first question. So here you will have C of S will be numerator is 3 squared by S plus S squared plus 3 squared. So it's S squared plus 9. I'm writing the denominator also this manner. So you can split it neatly by 1 by S minus S by S squared plus 3 squared. So if you apply inverse Laplace transform, it's 1 minus cos 3t. This is the equation for the undamped case. So this is straightforward. Alright. So now we go into week 11 contents. So we had seen the 3 equations of motion that govern the longitudinal dynamics. So now we know that there are 4 pairs of roots, and these 2 pairs of roots, 4 roots, 2 pairs of roots, and these 2 pairs are significantly away from each other. They are there's a big gap between these two, between the real components. Alright. So we can make nice approximations to separate these two. So one such approximation is the short period mode, where you assume u to remain constant. So when u remains constant, the first row and the first column are eliminated, and the other assumptions that follow because of the same u remains constant is that these 3 terms are also 0. So now when you apply all of these assumptions to the above equation, you get a second order approximation for the short period mode, which is this equation, and from that equate it to a typical second order system, and you get omega n and damping ratio zeta. Okay, so these are the 2 components that you get for the short period mode approximation. The next one is the phugoid mode or the long period mode approximation. Here you assume alpha to be constant. What happens here is that the second column and the third row are eliminated when you assume alpha to be 0. The other assumptions that follow because of the same alpha remains constant are zq and theta 1 are also 0. Now from this approximation you get another second order system from which you find out the natural frequency and the damping ratio. And the third assumption is that it's a pure pitching moment. What is a pure pitching moment? So pitch is basically theta was flight path angle plus alpha. So if it's a pure pitching, you assume flight path angle to be 0. It's just theta equals alpha, right? In this assumption, again you had just the q dot equations. The other 2 equations can be eliminated because you're assuming it to be just a pure pitching motion. And from that again you get a second order equation for which again you can find out the natural frequency and the damping ratio. This should be pure pitching. So this slide just summarizes the 3 second order equations, the natural frequencies and the damping ratio. So short period, phugoid and pure pitching. So now let's look at a few questions. So for an aircraft, the roots of the longitudinal characteristic For an aircraft, the roots of the longitudinal characteristic equation are as shown in the figure. So now there are 2 pairs of complex conjugate roots shown here. So this is minus 4 plus minus 2i, and here you have minus 0.002 plus or minus 0.1i. So which one is short period, which one is phugoid? Can you tell me that based on the discussion that we just had? Which is short period, which is long period? This is short period, right? The magnitude of the real part is larger here, and this is the long period. Okay, let's look at the first question. the roots for the short period mode are. We just discussed this, so it's this one. Natural frequency and damping ratio of the phugoid mode are respectively. So I'll just write down the roots. Plus or minus 0.1 I. So these are the roots. Now we need to find out the natural frequency and damping ratio. So please try to do it and then we'll solve it together. Just have to make the equation, right? So it's just s squared minus sum of roots into s plus product of roots equals 0. And then you can just plug in the roots and find out the equation equated to typical second order system and find it. So what is the second order system? Now it's straightforward from here. consider the following equation for a system. Find the range of k values necessary for dynamic stability of the system. So we have studied the Ruth criteria. So we have studied a couple of conditions from it. First one was that all the coefficients should be greater than 0. And the next one was the first column of the Ruth table should be, all the coefficients in the first column of the Ruth table must be greater than 0. So please try to find out using these two conditions. What are the conditions imposed on k? So one condition is straightforward, right? All the coefficients must be greater than 0. So you have 1 plus k should be greater than 0. So k should be greater than minus 1. So that is one condition. So what about the other condition? Make the Ruth table. So Ruth table is A, B, C, D, and then you have A1 here. Right? How do we find out A1? What is the formula to find out A1? So we had A1 equals minus 1 by B, and this A, C, B, D. So that is minus 1 by 3. So this is A, B, C, D. And we have 1, 3, 3, 1 plus Q. So now you should be able to find out pretty fast. So we just have 1 plus k minus 9 or minus 3 should be greater than 0. So we have minus 1 minus k plus 9 should be greater than 0 or k should be less than 8. This is your second condition. So these satisfy the conditions. Yeah. So with this we come to the end of today's session. If you have any questions, please ask. If not, we'll meet again for the next